You've been doing everything they said to do, and somehow you feel worse. Your body has a mandatory worsening protocol. Science doesn't call it failure. It calls it phase 1. Every repair your body has ever run began with a period of deliberate damage, controlled inflammation, and cellular demolition before a single new structure was laid down. The part most people never hear. Interrupting that process at its worst point is the one thing that ensures it never completes. Welcome to Sleepy Science Facts. The worsening was always the first chapter. Close your eyes. Let your breath find its own slow pace. Your body is already running its quiet repair. You only have to stay still. And now we begin. When your body sustains any injury, a cut, a bruise, a torn muscle, a surgical incision, the very first thing it does is not begin healing. It begins breaking down. Within seconds of damage, mast cells at the injury site release histamine and prostaglandins, two chemical signals that trigger immediate inflammation. Blood vessels dilate. Fluid rushes in. The area swells, reddens, and often hurts more than the original injury. This is not a malfunction. This is phase 1 of the only repair process the human body has ever run. The biological healing paradox begins at the very first moment. Before anything can be rebuilt, the tissue must first be made worse. That is where tonight begins. The inflammatory response that begins healing is orchestrated by the immune system with notable precision. Neutrophils, the body's first responder white blood cells, arrive at an injury site within minutes, sometimes as fast as 30 seconds after damage. They are not gentle. Neutrophils release enzymes called proteases that actively digest damaged tissue, cellular debris, and invading pathogens. This digestion process is destructive by design. The neutrophils are not trying to be careful. They are clearing the construction site. Studies published in the Journal of Leukocyte Biology confirm that this early, aggressive clearing phase is not optional. Without neutrophil-driven destruction of damaged tissue, the repair cells that follow have no clean substrate to work with. After neutrophils arrive, a second wave of immune cells called macrophages moves in. Macrophages perform two opposite functions in sequence, and the timing between them determines whether healing proceeds or stalls. In the first phase, macrophages behave as M1 phenotype cells, pro-inflammatory, aggressive, consuming dead tissue and releasing cytokines that maintain the inflammatory signal. Then, typically between days 2 and 4 for most soft tissue injuries, the same macrophages switch to M2 phenotype, anti-inflammatory, tissue building, releasing growth factors that call in repair cells. This macrophage polarization switch is one of the most studied transitions in wound healing biology. Missing or shortening the M1 phase disrupts the M2 phase that follows. Because the switch requires sensing the cleared wound environment the M1 cells created. The swelling that accompanies inflammation is not a side effect of healing. It is an active delivery mechanism. When blood vessels dilate and become more permeable, plasma proteins and immune cells flood the interstitial space around the injury. This creates edema, the visible, often painful swelling that makes people want to stop the process. But within that fluid is a carefully assembled chemical toolkit. Fibrinogen forms temporary scaffolding. Complement proteins tag debris for removal. Cytokines coordinate the sequence of cellular arrivals. Research on soft tissue injury has shown that artificially reducing early edema measurably delays the arrival of repair phase cells. The swelling carries the repair crew to the worksite. It is not incidental. It is the delivery. Pain during healing is not simply a signal that something is wrong. It is partly a mechanism that enforces rest for the repair process. Prostaglandins, released during the inflammatory phase, sensitize nociceptors, the nerve endings that detect pain. This sensitization, called peripheral sensitization, lowers the pain threshold around the injury, meaning stimuli that would normally be painless become painful. The biological purpose is protection. The heightened pain response discourages use of the injured area, reducing mechanical disruption to the early repair scaffolding. The pain of healing is therefore not separate from healing. It is part of the protocol. A body that felt fine during active tissue rebuilding would likely destroy what it was building. One of the most counterintuitive findings in repair biology is that the body does not simply remove damaged tissue. It deliberately creates more damage in a controlled zone around the original injury. This process, called cellular debridement, involves macrophages and neutrophils extending their work beyond the initial wound margin. They release reactive oxygen species, chemically aggressive molecules that destroy additional cellular material in a ring around the injury. This secondary clearing zone ensures that the scaffolding laid down in the next phase has clean, healthy tissue at its borders. The body makes the wound temporarily larger, so the repair that follows has a stable foundation. Controlled destruction precedes every stable structure. The three phases of tissue healing: inflammation, proliferation, and remodeling are not sequential steps that follow each other neatly. They overlap in a dynamic, sometimes messy progression. The proliferation phase, in which new tissue is actively constructed, begins while the inflammatory phase is still running. Fibroblasts arrive at the wound site as early as day 2, laying down new collagen, while neutrophils are still clearing debris. This overlap means a healing body is simultaneously tearing down and building up, in the same location, at the same time. From the outside, this looks like persistent pain, swelling, and dysfunction. From the inside, it is coordinated, parallel processing, the biological equivalent of demolishing one floor of a building while framing the next. Collagen is the primary structural protein of almost all human connective tissue. Skin, tendons, ligaments, bone matrix, and scar tissue. During the proliferation phase of wound healing, fibroblasts produce collagen at an accelerated rate, laying down type 3 collagen first, a flexible, weaker form that acts as a temporary framework. This early collagen is not the final product. Over the following weeks and months, the remodeling phase slowly replaces type 3 collagen with type 1, stronger, denser, more organized. Research from the Wound Healing Society identifies the collagen transition as one of the slowest parts of the entire healing cascade. The tissue that looks and feels healed at week 2 may be less than 30% through its actual structural repair. One reason healing often feels worse before it improves is the phenomenon of central sensitization, a temporary recalibration of the spinal cord and brain's pain processing circuits in response to prolonged peripheral pain signals. When an injury sends pain signals continuously for several days, the central nervous system can amplify its processing of those signals, lowering the threshold for pain perception across a broader area. This means a person healing from a shoulder injury may begin to feel pain in their neck, upper back, or arm, areas not directly injured. This spread of perceived pain is not evidence that the injury has worsened. It is evidence that the nervous system is prioritizing the healing site with increased vigilance, a protective amplification that typically resolves as the repair progresses. The inflammatory phase of healing produces chemical signals that cross the blood-brain barrier and alter brain function, helping explain why healing from physical injury often produces fatigue, low mood, brain fog, and disrupted sleep. Cytokines such as interleukin-1 beta and tumor necrosis factor alpha, released during active tissue repair, act on the hypothalamus to trigger what researchers call sickness behavior. Reduced activity, increased sleep drive, appetite changes, and social withdrawal. This is not depression. It is a conserved biological program, documented across nearly all vertebrates, that redirects metabolic resources toward the active repair process. A body that feels cognitively clouded during healing is running an ancient protocol, not failing. 10 facts in. The answer is already visible. The process of healing muscle tissue differs from healing skin or connective tissue in one key way. Muscles contain satellite cells, specialized stem cells that lie dormant against muscle fibers until damage activates them. When muscle fibers are torn, whether through exercise, injury, or disease, satellite cells are chemically awakened by the same inflammatory signals that trigger general wound healing. They proliferate, differentiate into muscle precursor cells called myoblasts, and fuse either to damaged fibers to repair them or together to form new fibers. This process, called muscle regeneration, is why resistance exercise produces muscle growth. The deliberate, controlled damage of training activates satellite cells, and the subsequent repair produces fibers that are thicker and stronger than the ones that were destroyed. The Jarisch-Herxheimer reaction, named after the dermatologists who first described it in the 1890s, is one of the most documented examples of the body worsening as a direct result of treatment working. When antibiotics are administered for spirochete infections such as syphilis, Lyme disease, or leptospirosis, the rapid die-off of bacteria releases large quantities of bacterial cell wall fragments and endotoxins into the bloodstream. The immune system responds with an acute inflammatory surge. Fever spikes, chills, muscle pain, and a worsening of all symptoms. This reaction typically peaks within 2 to 8 hours of treatment and resolves within 24. The worsening is caused entirely by the treatment working. The healing agent is doing exactly its job, Bone healing after a fracture follows a repair sequence that makes the temporary worsening of structural integrity visible in X-rays. In the first 2 weeks after a fracture, the body forms a soft callus, a mass of cartilage and immature connective tissue that bridges the broken bone ends. This callus appears less organized and structurally weaker than the original bone. The bone is, at this stage, genuinely weaker at the fracture site than it was before the break. Over the following weeks, the soft callus is replaced by hard callus, calcified, dense, and increasingly strong. Research from NIH-funded orthopedic studies consistently shows that peak pain and functional impairment in fracture healing correlate with the soft callus phase, not the break itself. The nervous system undergoes its own version of damage before repair following injury. When peripheral nerves are damaged, cut, compressed, or stretched, the damaged segment undergoes Wallerian degeneration, a systematic breakdown of the axon and its myelin sheath distal to the injury site. Schwann cells, which normally maintain the myelin coating, shift into a repair phenotype and begin clearing the debris of the degenerated nerve. This clearing phase, which can take days to weeks depending on the nerve's length, is a prerequisite for nerve regrowth. Without complete Wallerian degeneration, regenerating axons have no cleared pathway to grow into. The nerve has to fully fall apart along its injured segment before it can regrow, making the period of numbness not a sign of permanent damage, but of active preparation. The immune system's role in wound healing is not limited to the injury site. Systemic immune activation during significant tissue repair pulls resources from other immune functions, temporarily reducing the body's capacity to respond to unrelated infections. This is why people healing from surgery, major injury, or illness are more vulnerable to secondary infections during recovery. The body is not failing at immune defense. It is triaging. Resources are redirected toward the active repair priority. A 2024 study in Nature Reviews Immunology described this reallocation as the immune system operating in a triage mode conserved across hundreds of millions of years of vertebrate evolution. The body accepts temporary vulnerability in one area to complete repair in another. Delayed onset muscle soreness, known as DOMS, is one of the most familiar everyday experiences of the healing paradox. After unaccustomed exercise, especially eccentric movements like walking downhill or lowering weights, muscles do not hurt immediately. The soreness typically peaks between 24 and 72 hours after the activity. This delay occurs because DOMS is not caused by the exercise itself, but by the inflammatory response to the micro-tears the exercise created. As neutrophils arrive to clear damaged tissue and fibroblasts begin laying down repair scaffolding, the chemical mediators of inflammation sensitize pain receptors in the muscle. The soreness is the repair in progress, arriving on a delay. The hardest days after a training session correspond to the most active phase of muscle rebuilding. Skin healing involves a particularly visible version of the worsening before improvement cycle, the scab. When a wound forms, the blood clotting cascade creates a fibrin mesh that traps platelets and red blood cells, forming a temporary seal. This scab protects the wound but is not the repair. It is the cover over the active construction underneath. in the days beneath a scab. Keratinocytes migrate across the wound bed. Macrophages clear debris, and fibroblasts lay down new dermal tissue. The scab itself must eventually be dissolved and shed. If removed prematurely, which disrupts the tissue migrating underneath, the healing process resets to an earlier phase. The protective structure that looks like healing is actually the cover story over something more complex. Psychological healing follows the same phase structure as physical healing, with documented neurobiological parallels. Following acute psychological trauma, the stress response system, centered on the hypothalamic pituitary adrenal axis, enters a heightened activation state, analogous to the inflammatory phase of tissue repair. Cortisol and norepinephrine flood the system. Memory consolidation is disrupted. Emotional regulation becomes less available, and the nervous system remains in a state of elevated vigilance. This period is characterized by heightened symptoms: intrusive thoughts, hyperarousal, emotional flooding. Neuroscience research from the National Institute of Mental Health consistently identifies this acute activation phase as a necessary precursor to the neural remodeling that follows in recovered individuals. The worsening is the system mobilizing, not the system failing. The gut microbiome undergoes its own version of the healing paradox during recovery from dysbiosis, a disruption to the normal microbial population. When the gut microbiome has been disturbed by antibiotics, illness, or dietary disruption, the recolonization process initially involves competitive exclusion. Beneficial bacterial strains outcompeting depleted populations for intestinal wall-binding sites. This competition temporarily increases gut motility, bloating, gas production, and intestinal discomfort. People attempting to restore their microbiome through probiotics or dietary changes frequently experience a 2 to 4 week period during which digestive symptoms worsen before improving. Research from the Human Microbiome Project confirms this transitional dysregulation as a marker of active recolonization rather than treatment failure. The disruption is the restoration in progress. Fever, the body raising its core temperature above the normal range of 97 to 99 degrees Fahrenheit, is one of the most studied examples of a healing mechanism that feels like a worsening. Fever is not a malfunction of thermoregulation. It is a deliberate, energy-expensive immune strategy. At elevated temperatures, the replication rates of many pathogens slow significantly, while phagocytic immune cells become more active. The metabolic cost is substantial, approximately 13% more energy per degree of elevation. The feeling of fever, chills, aching, weakness, cognitive slowing is caused by the same cytokine signals that are driving the immune response. The sicker you feel during a fever, in most cases, the harder your immune system is working. The liver undergoes a process called the acute phase response during significant infection, injury, or inflammation. Upon receiving cytokine signals from the injury site, liver hepatocytes rapidly change their protein synthesis profile, reducing the production of normal transport proteins like albumin and increasing the production of acute phase proteins such as C-reactive protein, fibrinogen, and complement factors. These proteins circulate through the bloodstream to support immune function at the injury site. The reduction in albumin means that, during active healing, the body temporarily runs lower levels of proteins that support general function, contributing to fatigue, fluid retention, and reduced tolerance for physical or cognitive stress. The body has repurposed its factory for the emergency order. One of the most precise examples of mandatory temporary worsening in biology is the process by which bones become stronger through exercise. Mechanical loading, walking, running, resistance training creates microscopic cracks in bone called microfractures. These cracks trigger the same osteoclast-osteoblast repair cycle that responds to fractures. Osteoclasts first dissolve the damaged bone matrix. Then osteoblasts deposit new, denser bone. The central discovery from bone biology research is that bone must be slightly damaged to become stronger. A bone never subjected to microfracture loading does not trigger the osteoblast response, and therefore does not increase in density. Controlled, repeated damage followed by adequate repair time is the only known mechanism for building stronger bones. Sleep is one of the most active phases in the body's ongoing repair and maintenance cycle. During wakefulness, neuronal activity produces metabolic waste products, including tau proteins and amyloid beta. The glymphatic system, the brain's waste clearance network, appears to flush these products from the brain's interstitial spaces most efficiently during slow-wave sleep. Research from the University of Rochester, primarily in animal models with growing human evidence, suggests the glymphatic system may increase its clearance activity significantly during sleep. The brain allows metabolic byproducts to accumulate through the day because it will address them during the quiet of night. The daily biological debt is not neglect. It is deferred maintenance, scheduled for the dark hours. Surgical healing provides a highly controlled context in which the worsening before improvement pattern is clinically predictable and well documented. Surgeons deliberately create tissue damage to address underlying pathology, cutting through skin, muscle, and sometimes bone to reach and repair what lies beneath. In the days following surgery, patients experience peak pain not at the moment of incision, but during the early inflammatory phase of healing, when prostaglandins are highest, swelling is maximal, and the nervous system is most sensitized. This post-surgical inflammatory peak is considered a positive prognostic sign. A wound that does not inflame adequately in the first 72 hours is more likely to develop complications or slower healing. The expected worsening is the evidence of repair mobilizing. 25 facts in. A pattern has become clear. Not one of the body's major repair systems. Skin, bone, muscle, nerve, immune, brain, microbiome initiates reconstruction without first running a phase of deliberate clearing, controlled damage, or systemic mobilization that produces symptoms worse than the original problem. This is not evolutionary accident. It is the only known architecture for repair that works at the complexity of living tissue. The central question reaches into every domain where repair occurs. Why does the body run a mandatory damage protocol before every act of repair? And what breaks when we interrupt it? What the next arc follows is the cost of interruption, and why the body has no workaround. Right now, something in your body is mid-repair. Not metaphorically, somewhere in your tissue right now. Macrophages are switching phases. Collagen is being laid. Inflammatory signals are quieting as repair signals rise. You have been carrying facts about this for 25 minutes. Let them settle now, not as information, but as something that already belongs to the way you understand your own body. The question that opened, what happens when the protocol is interrupted, is not yet answered. That is where the next arc begins. Notice your breath. The system is already demonstrating something. Now we continue. When the inflammatory healing response is suppressed in the early phase, as happens with high-dose corticosteroids, NSAIDs administered immediately after injury, or aggressive icing protocols, the short-term result is reduced pain and swelling. The long-term result is frequently delayed healing and reduced final tissue quality. A study in the Scandinavian Journal of Medicine and Science in Sports demonstrated that athletes who used ibuprofen immediately after muscle injury had reduced pain at day 5, but measured lower muscle regeneration at day 30 and reduced cross-sectional fiber area at 12 weeks. The body was convinced the emergency was over. It downregulated the repair response. The pain signal, suppressed, had been carrying information the healing system needed. The concept of hormesis, the biological phenomenon in which low doses of a stressor produce adaptive benefit, is one of the foundational principles explaining why controlled damage precedes repair. Hormesis is documented across species from bacteria to humans. Small doses of radiation, heat stress, oxidative compounds, and mechanical force all trigger protective responses when followed by adequate recovery. The dose-response curve is J-shaped. A small dose stimulates improvement, a large dose causes harm, and zero dose produces no adaptation. Exercise physiology is built on hormetic principles. The training stimulus has to damage the system slightly, or the repair response that produces improvement is never triggered. The body does not strengthen without being challenged past its current capacity. Psychological therapy, particularly trauma-focused approaches such as EMDR, prolonged exposure, and somatic processing, consistently produces a period of symptom intensification before improvement. A pattern so reliable, it has been given a clinical name: the therapeutic dip. Research published by Safran and colleagues, and expanded in subsequent meta-analyses, found that clients who stayed through a therapeutic dip showed better long-term outcomes than those whose therapy avoided distress activation. The neurobiological explanation involves the reconsolidation window. When a traumatic memory is reactivated, the synaptic connections encoding it temporarily destabilize, becoming modifiable before restabilizing in a less reactive form. The destabilization feels like worsening. It is the rewrite in progress, the remodeling phase of tissue healing. The final, longest phase involves the replacement of the temporary type 3 collagen scaffold with the stronger, more organized type 1 collagen. This phase begins as early as 3 weeks after injury and continues in significant tissue repair for up to 2 years. During remodeling, the tissue may intermittently feel tight, stiff, and sensitive as new collagen matures and organizes along lines of mechanical stress. This functional remodeling, where collagen aligns according to the forces the tissue regularly experiences, is how healed tissue gains the specific properties it needs. Scar tissue that is never loaded or stretched remodels differently than tissue that is regularly used. Neuroplasticity, the brain's capacity to reorganize its neural connections in response to learning, injury, or experience, follows the same mandatory disruption pattern as physical tissue repair. Following brain injury, stroke, or significant psychological trauma, neuroplasticity does not proceed through simple addition of new connections. It proceeds first through synaptic pruning, the elimination of existing connections in the affected area. Research from MIT's Picower Institute confirms that pruning is a prerequisite for adaptive rewiring. Without clearing the old circuit architecture, the brain cannot lay new pathways efficiently. The period following brain injury, in which cognitive function declines before stabilizing and then improving, corresponds to the pruning before rewiring phase. The brain, like muscle and bone, requires its own controlled demolition. Cells undergo a form of deliberate self-destruction as part of normal tissue maintenance and healing. Apoptosis, programmed cell death, is a highly regulated process in which a cell dismantles its own components in an orderly sequence, packages the remnants into neat membrane-bound bodies, and signals neighboring cells to consume the debris. Apoptosis is integral to wound healing. It removes damaged cells that would otherwise become necrotic, eliminates excess inflammatory cells after the acute phase, and clears the way for new tissue organization. A body unable to run apoptosis efficiently, as seen in certain inflammatory diseases, often cannot resolve healing properly. The experience of emotional grief follows a biological trajectory with parallels to tissue healing that neuroscience has been documenting in increasing detail. Acute grief activates the anterior cingulate cortex, insula, and amygdala, brain regions involved in pain processing, visceral sensation, and threat response. Neuroimaging studies show that early grief is accompanied by elevated activity in these regions that gradually declines over months in people who recover adaptively. The early phase, characterized by intrusive thoughts, emotional flooding, physical chest pain, and disrupted sleep, corresponds to the inflammatory equivalent phase in neural healing. High activation, high cost, high disruption. The brain does not repair the neural representation of loss by minimizing the experience. It repairs it by processing fully. Exercise-induced immune suppression is a well-documented temporary worsening of immune function following intense physical exertion. In the hours after a demanding bout of exercise, the concentration of circulating lymphocytes, immune cells involved in pathogen surveillance, temporarily drops below baseline. Natural killer cell activity decreases. This window of reduced immune function, called the open window hypothesis, lasts approximately 3 to 72 hours, depending on exertion, intensity, and duration. During this window, athletes are more vulnerable to upper respiratory infections. The same intense exercise that, through repeated hormetic cycles, eventually strengthens immune function, temporarily weakens it in the immediate recovery period. The path to greater immune resilience runs through the open window. The process of learning permanently changes the brain's physical structure, and the change requires a phase of instability before consolidation. When a new skill or piece of information is encoded, synaptic connections are potentiated through long-term potentiation, a process involving calcium influx, receptor trafficking, and protein synthesis that strengthens specific synapses. But before consolidation is complete, the memory is in a labile, vulnerable state, more easily disrupted, confused, or lost. Sleep is necessary to complete consolidation because it provides the offline quiet in which protein synthesis required for stable long-term potentiation finishes. The fact you learned this morning may have been slightly fragile by evening. By morning, after slow-wave sleep, it will be more durable. The human immune system maintains immunological memory, the capacity to respond faster and more effectively to a pathogen it has encountered before. This memory is built through vaccination and infection by a process that requires the initial immune response to run to completion, including the resolution phase. Vaccines work by triggering the full inflammation and resolution cycle without the costs of actual infection. The immune system mounts an inflammatory response, produces antibodies and memory cells, then resolves the inflammation. The soreness, fatigue, and mild fever that accompany many vaccinations are evidence of this response running. Suppressing those symptoms with anti-inflammatories may, research suggests, slightly reduce the strength of the subsequent immune memory. Angiogenesis, the formation of new blood vessels, is a key component of wound healing that requires the destruction of existing vessel architecture before new growth can occur. During the proliferative phase, the body must break down the fibrin clot formed during hemostasis to allow new capillaries to grow into the wound bed. This clot dissolution, driven by plasmin and matrix metalloproteinases, produces an intermediate state in which the wound has less structural integrity than it had under the clot. The new capillaries that grow into this space are initially fragile and permeable, contributing to continued redness and warmth. The visible signs suggesting ongoing inflammation may coincide with the most active phase of vascular reconstruction. The body's response to chronic stress follows a worsening trajectory before any form of adaptation is possible. When the hypothalamic pituitary adrenal axis is persistently activated by ongoing stressors, it produces elevated cortisol, disrupted sleep architecture, heightened vigilance, and reduced working memory capacity. But when sufficient recovery is provided, rest, reduced demand, adequate sleep, social safety, the system does not simply return to its previous baseline. It recalibrates. The recalibration period involves a temporary further disruption. The nervous system must downregulate its heightened vigilance, which can feel like lethargy, emotional release, or vulnerability. The recovery from chronic stress can temporarily feel like a collapse before it feels like restoration. Tendons heal more slowly than muscle and are more likely to produce prolonged pain during the healing process because of a fundamental difference in cellular composition. Tendons are hypovascular. They have a limited blood supply and contain a low density of the tenocytes responsible for collagen repair. When tendon tissue is damaged, the inflammatory response is present but attenuated compared to well-vascularized tissue. Repair proceeds more slowly, and the remodeling phase extends for 6 months to 2 years in major tendon injuries. The prolonged pain that accompanies tendon healing reflects the slow, under-resourced collagen remodeling process, working at the pace set by the tissue's own biology, not the pace the person experiencing it hopes for. The healing of the intestinal epithelium, the single cell-thick lining of the gut, involves a process called restitution, in which epithelial cells at the wound edge migrate laterally to cover the damaged area before new cell proliferation begins. During restitution, the covering cells become flattened and spread thin, temporarily reducing their digestive function and barrier integrity. The gut is, during this phase, simultaneously healing and less functional than normal. This explains a commonly observed pattern. People recovering from gastrointestinal illness often feel their digestion is erratic for days after they appear recovered. The surface has been covered. The deeper restoration of normal architecture takes considerably longer. 40 facts in. A second pattern is emerging alongside the first. Not only does worsening precede repair, the worsening is the mechanism. The inflammation is not incidental to clearing. It is the clearing. The pain is not a side effect of healing. It is a protective enforcement of the conditions healing needs. The disruption is not a symptom to suppress. It is the signal that tells the system what to build next. What the second half of tonight follows is the question this raises. If the worsening is the mechanism, what happens when it is interrupted, suppressed, or misdirected? The question is not only about biology. You may already be carrying it. You've been listening for a while now, moving through these mechanisms. Take a slow breath. Notice that your body is not just the subject of what you've been hearing. It is doing some version of this right now. Somewhere, something is being cleared so something else can be built. We're moving through healing science together. You and the quiet. And we'll keep going. Slowly. Physical rehabilitation research has identified a specific pattern called the reactive stage, a period in musculoskeletal recovery when tissue, subjected to load too early, flares back into acute inflammation. Studies on patella and Achilles tendon recovery document reactive tendinopathy, a return to the acute inflammatory phase triggered by mechanical overload before the remodeling phase has completed. The tissue's capacity to tolerate load is lower during active remodeling than it was before injury, meaning the healing structure is temporarily more vulnerable than the original one. This is the cost of interruption. Not just delay, but regression to an earlier phase with the timeline reset. The body cannot skip the sequence. It can only repeat it from the interrupted point. One of the most consistent findings in psychotherapy research is that emotional avoidance, the suppression or minimization of distressing emotional experience, reduces short-term discomfort but extends the duration and severity of psychological difficulty. Research by Stephen Hayes identifies experiential avoidance as a process underlying anxiety, depression, PTSD, and chronic pain. The neural mechanism involves the prefrontal cortex suppressing amygdala activation, effective in the moment, but preventing the amygdala from completing its processing of the threat signal. The emotional pain that is consistently avoided does not resolve. it remains encoded at full activation strength, requiring repeated suppression. What is not processed is not healed. It is deferred. The phenomenon of post-traumatic growth, documented by psychologists Richard Tedeschi and Lawrence Calhoun since the 1990s, describes the meaningful positive psychological change that emerges in some individuals following significant adversity. Post-traumatic growth is not the absence of pain or the return to pre-trauma functioning. It is a new configuration, only possible after the old configuration has been disrupted. Tedeschi and Calhoun's research, updated through longitudinal studies in the 2020s, consistently finds that post-traumatic growth correlates with degree of initial distress experienced. People most disrupted by trauma showed the greatest capacity for growth, provided they received adequate support and processing time. The disruption is a precondition for the growth, not a step that can be skipped. The remodeling phase of wound healing is sensitive to mechanical loading, the forces the healing tissue experiences during recovery. Research in mechanobiology has established that fibroblasts align their collagen deposits along the lines of tension they detect in the wound environment. Scar tissue in an immobilized limb remodels differently than scar tissue that is regularly moved and loaded. A scar that receives appropriate mechanical stimulus during remodeling becomes more functional, more extensible, and more similar to uninjured tissue than one protected from all stress. The body uses mechanical information provided by movement to build what the tissue will need. Rest is required, but permanent protection defeats the remodeling purpose. Sleep disruption is one of the most well-documented consequences of active healing, and also one of the factors that most significantly impairs the healing process itself, creating a difficult cycle. Inflammatory cytokines elevated during the acute healing phase, particularly IL-1 beta and TNF-alpha, directly disrupt normal sleep architecture, reducing slow-wave sleep and fragmenting REM. At the same time, slow-wave sleep is the primary window for growth hormone release, which drives tissue repair and immune cell production. A person healing from injury who sleeps poorly produces less growth hormone and fewer repair cells. The same inflammation that signals healing impairs the sleep that healing requires. The body navigates this cycle best when behavioral support for sleep is consistently maintained. The process of addiction recovery involves a neurobiological worsening phase, as precisely choreographed as any physical tissue repair. Chronic substance use downregulates the brain's dopaminergic reward circuitry, reducing the density of dopamine receptors in the nucleus accumbens and prefrontal cortex. When substance use stops, the understimulated reward system produces a period of anhedonia, the inability to experience pleasure from activities once rewarding. This phase, documented in neuroimaging studies of individuals in early abstinence, typically lasts 4 to 12 weeks as receptor density slowly recovers. It is the neurobiological equivalent of the inflammatory phase. The most uncomfortable period of recovery corresponds to the most active phase of receptor remodeling. The absence of pleasure is the system rebuilding its capacity. Rehabilitation after orthopedic surgery follows a carefully staged return-to-function protocol, specifically because the body's healing phases must be respected in sequence. In the first phase, immediately after surgery, the goal is not to rebuild strength, It is to manage inflammation and protect the initial repair. In the second phase, as inflammation resolves, range of motion is gently restored. Only in the third phase, weeks to months later, does progressive loading to rebuild strength begin. Physical therapists who advance patients too quickly, particularly by loading tissue before the collagen scaffold has matured, risk disrupting the remodeling that is still in progress. The protocol is conservative because the biology being navigated has its own timeline that does not negotiate. The skin's response to sun damage at the cellular level provides a small-scale demonstration of the mandatory repair sequence. When ultraviolet radiation damages the DNA in skin cells, the cells undergo a p53-mediated checkpoint response. The cell pauses its normal cycle, attempts DNA repair, and if repair is not possible, initiates apoptosis. The visible result is the redness, warmth, and peeling of mild sunburn. The peeling skin is the body completing the apoptosis process, shedding cells too damaged to repair, making way for new keratinocytes migrating up from the basal layer. Removing peeling skin prematurely disrupts the barrier function being rebuilt beneath it. The shed is part of the sequence. The nervous system's recovery from chronic overactivation, whether from prolonged stress, burnout, or sustained trauma exposure, does not proceed through a simple return to previous function. It proceeds through a recalibration that involves a period of reduced capacity before new capacity emerges. Some frameworks in nervous system research describe recovery from shutdown as passing through a period of heightened activation before arriving at a calmer, more regulated state. The nervous system may climb back toward regulation through states it previously experienced on the way down. The path of recovery traces the path of the injury in reverse, which is why early recovery can feel like the difficulty returning, not leaving. Halfway through 100 facts about the biology of healing, the mandatory damage protocol has revealed itself at every scale the body operates on, from individual cell apoptosis to bone remodeling to neuroplastic rewiring to the systemic recalibration of the stress response. Every system uses the same logic. Clear, then build. Disrupt, then reorganize. The central question has not yet been answered in its sharpest form. What breaks when the protocol is interrupted? Not just delayed, but broken. The second half follows the cases where interruption becomes its own kind of damage. The question you are carrying is not abstract. It lives in every tissue that has ever tried to repair, while something kept the clearing from finishing. What just opened? The question of what happens when the clearing can't complete is not only a biology question. You may be carrying a version of that right now. Something that has been trying to move through its phase and keeps being interrupted. By the next day, by what has to happen next, by the reasonable, understandable insistence that you feel better now. Notice your breath. Your body knows what it's doing in the quiet. The second half follows what happens when the protocol is allowed to finish. Now we continue. When wound healing is repeatedly interrupted by mechanical disruption, a cut that is constantly reopened, a tendon reloaded before repair is complete, the tissue enters a state called chronic wound formation. In a chronic wound, the inflammatory phase restarts with each disruption before the previous cycle has resolved, creating a perpetual loop of acute inflammation with no transition to proliferation. Chronic wounds contain elevated levels of proteases, the same enzymes that clear debris in the acute phase, in concentrations that now break down the new collagen being produced. The tissue is simultaneously trying to build and being chemically prevented. The clearing mechanism has become the obstacle. Excessive or prolonged inflammation, chronic inflammation, is the clinical manifestation of the body's repair protocol failing to resolve. In healthy acute inflammation, anti-inflammatory signals, including interleukin-10 and lipid mediators called resolvins, progressively quiet the inflammatory response as the clearing phase completes. In chronic inflammation, these resolution signals are insufficient or overwhelmed. The macrophages do not complete their M1-M2 switch. The neutrophils continue releasing proteases. The tissue remains in perpetual attempted repair that cannot advance to construction. Chronic inflammatory conditions, rheumatoid arthritis, inflammatory bowel disease, atherosclerosis, certain forms of depression, all involve this failure of resolution, not an excess of the initial response. The opioid pain management approach, widely used for decades following surgical and injury-related pain, has been found to interfere with the healing process in ways not initially anticipated. Opioids, beyond their analgesic effects, directly suppress immune function. They reduce natural killer cell activity, inhibit macrophage migration, and decrease pro-inflammatory cytokine production. Animal model research published in the Proceedings of the National Academy of Sciences found that chronic opioid administration following nerve injury paradoxically prolonged pain hypersensitivity, in part because the suppressed immune response allowed ongoing neuroinflammation to persist without resolution. The healing paradox is visible at the evolutionary level in the phenomenon of fever. Fever is metabolically expensive, approximately 13% more energy per degree Fahrenheit of elevation. Evolution has maintained fever across 400 million years of vertebrate history, despite this cost. Because the survival advantage of the heightened immune response it enables outweighs the metabolic expense in most contexts. The fact that fever has been preserved at significant metabolic cost across virtually every warm-blooded species on Earth is perhaps the clearest evidence that the biology of worsening before healing is not a design flaw. It is a core feature of the most successful biochemistry life has produced. Autophagy, the cellular process by which a cell digests its own damaged organelles and proteins, is one of the most fundamental examples of self-directed damage enabling repair. When a cell detects a dysfunctional mitochondrion or protein aggregate, it encloses the structure in a membrane vesicle called an autophagosome and delivers it to a lysosome for digestion. The digested components are recycled into new cellular building blocks. Autophagy is activated by cellular stress, nutrient deprivation, infection, oxidative damage, and is considered a primary quality control mechanism of cellular health. The 2016 Nobel Prize in Physiology was awarded to Yoshinori Osumi for this work. The biology of bone density loss and recovery provides a measurable window into the cost of prolonged protection. When a limb is immobilized, in a cast, splint, or through non-weight-bearing protocols, osteoclast activity exceeds osteoblast activity within 48 hours, beginning the process of disuse osteoporosis. Bone density can decrease by 1 to 2% per week of complete immobilization, without mechanical signals indicating the bone will be needed. The body does not invest in maintaining density beyond what current repair requires. The bone is simultaneously healing the fracture and losing structural mass in surrounding tissue. Protection has a biological cost proportional to its duration. The relationship between stress and immune function follows an inverted U-curve that mirrors the hormetic model of healing. Acute, time-limited stress, the kind generated by a single demanding challenge followed by recovery, activates the immune system, increasing lymphocyte and natural killer cell activity. But chronic, unresolved stress, the kind that continues without the recovery phase, progressively suppresses immune function through the sustained elevation of glucocorticoids. The immune system, like muscle and bone, requires the cycle of challenge and recovery to maintain optimal function. Perpetual stress, like perpetual immobilization, prevents the repair that the stress was meant to initiate. Liver regeneration is one of the most studied examples of organ-level repair, and it provides a clear illustration of why mass must be temporarily sacrificed for capacity to be restored. The liver is the only human organ with significant regenerative capacity, able to regrow to approximately its original size after surgical removal of up to 70% of its mass. This regeneration involves hepatocytes near the resection margin re-entering the cell cycle and proliferating. During active regeneration, liver function is reduced. Metabolic, detoxification, and protein synthesis capacities operate below normal, while cellular energy is directed toward proliferation. The organ is building at the cost of its normal operational efficiency. The human body maintains a constant low-level repair process called tissue homeostasis, the ongoing replacement of cells that have completed their functional lifespan. The skin's outer epidermal layer is replaced approximately every 2 to 3 weeks. The intestinal epithelium renews completely every 3 to 5 days. This continuous maintenance repair runs on the same phased logic as acute healing. Old cells must complete apoptosis and be cleared before new cells populate the space. The body is never fully at rest. It is engaged in ongoing demolition and construction at every scale. The concept of allostatic load describes the cumulative cost to the body of repeated cycles of stress mobilization without adequate recovery. Developed by Bruce McEwen and colleagues at Rockefeller University, the model distinguishes between allostasis, the body's healthy adaptive responses to challenge, and allostatic load, the wear that accumulates when adaptive systems are chronically overactivated. High allostatic load is associated with accelerated cellular aging, elevated baseline inflammation, disrupted HPA axis regulation, and increased risk across cardiovascular, metabolic, and neurological disease categories. The body can run the mandatory worsening protocol many times. What it cannot sustain indefinitely is the protocol without the recovery phase that completes it. Resolvins, lipid-derived signaling molecules produced from omega-3 fatty acids, are among the most actively researched compounds in the biology of inflammation resolution. Identified by Charles Sirhan's laboratory at Harvard Medical School, Resolvins belong to a class of molecules called specialized pro-resolving mediators. These molecules do not simply suppress inflammation. They actively drive the resolution process, promoting clearance of apoptotic neutrophils, restoring vascular integrity, reducing pain sensitization, and signaling the tissue that the clearing phase has completed. Research in 2024 described impaired SPM production as a factor in several chronic inflammatory conditions. The end of the worsening phase is not passive. The body signals that clearing is done. Post-traumatic growth distinguishes clearly between resilience, returning to previous function, and growth, which is a genuine expansion of psychological capacity only available after disruption. Richard Tedeschi's longitudinal research identifies 5 domains in which post-traumatic growth most commonly occurs: personal strength, new possibilities, relating to others, appreciation for life, and spiritual or existential understanding. None of these domains expand from the disruption itself. They expand from the meaning-making process that follows adequate processing of the disruption. The growth is not in the trauma. It is in the narrative the healed nervous system constructs after the clearing phase completes. The worsening must be fully experienced to become the foundation. The fascia, the connective tissue network that surrounds and connects muscles, organs, and bones throughout the body, undergoes its own healing process that is slower and less well understood than muscle or bone repair, but increasingly recognized as significant. Fascia is richly innervated, meaning fascial damage produces pain disproportionate to the size of the injury. Fascial healing involves the same collagen remodeling sequence as other connective tissue. But the fascial network's body-spanning architecture means that tension introduced at one site propagates through the network. This is why a hip injury can produce knee or shoulder pain. The blood-brain barrier, the selective cellular border that protects the brain from circulating pathogens and most immune cells, temporarily increases its permeability during active systemic inflammation. This regulated permeability allows certain immune signaling molecules to cross and communicate the body's systemic state to the brain. The neuroinflammation that results is responsible for the sickness behavior noted earlier: fatigue, cognitive slowing, social withdrawal, increased sleep drive. Research from the University of Virginia, published in 2023, found that this neuroimmune communication channel is more sophisticated than previously understood, with the brain actively monitoring the systemic inflammatory response through glymphatic and lymphatic connections. One of the most quietly significant findings in sleep medicine is that emotional memory consolidation during REM sleep involves a process that reduces the emotional charge of encoded memories, not their content, but their affective intensity. Research from Matthew Walker's laboratory at UC Berkeley demonstrated that REM sleep appears to strip amygdala activation from the memory trace while preserving narrative content, so that a memory encoded with fear or grief may be retrieved the following day with less physiological arousal. This nightly emotional reprocessing is one proposed mechanism by which adequate sleep gradually reduces the acute intensity of psychological pain over time. The memory remains. The acute sting decreases. Hormones play a precise coordinating role in the healing process that extends beyond any single tissue type. Growth hormone, released in pulses during slow-wave sleep. stimulates satellite cell activation in muscle, promotes collagen synthesis in connective tissue, and supports immune cell production. Insulin-like growth factor 1, produced by the liver in response to growth hormone signaling, carries the anabolic instruction to peripheral tissues. Cortisol, central to the acute stress response, must decrease during recovery phases to allow growth hormone and IGF-1 to work effectively. The two systems are reciprocally regulated. Healing requires the right hormonal environment, which sleep and recovery are designed to provide. Wound contraction, the process by which healing wounds gradually pull their edges together, involves specialized cells called myofibroblasts, which contain smooth muscle filaments and can generate significant contractile force. Myofibroblasts differentiate from fibroblasts under the influence of TGF-beta and mechanical tension, and their contraction is responsible for the visible shrinkage of healing wounds over days to weeks. In normal healing, myofibroblasts complete their work and then undergo apoptosis, clearing the field once wound closure is achieved. In pathological healing, hypertrophic scarring or keloid formation, myofibroblasts persist beyond the point of closure, producing raised, dense scar tissue. Clearing failed to complete. The concept of the wound environment, the specific chemical and cellular milieu surrounding healing tissue, has emerged as a central concern in regenerative medicine, because the same cell types behave very differently depending on the signals they receive. Macrophages in a pro-inflammatory environment activate tissue-destructive programs. The same macrophages in a pro-resolving environment activate tissue-constructive programs. Interventions designed to change the wound environment, rather than suppress specific cell types, hold increasing promise for improving healing outcomes. The question in regenerative biology increasingly centers not on which cells to add, but on what signals to provide the cells already present to complete their natural progression. The social environment profoundly influences the pace and quality of biological healing, a connection documented through multiple physiological mechanisms. Social isolation elevates circulating cortisol and inflammatory cytokines, which delays the M1 to M2 macrophage transition and impairs sleep architecture. Perceived social support is associated with lower baseline inflammation, faster wound healing in controlled studies, and better outcomes following surgery and illness. Research from Ohio State University found that marital conflict measurably slowed wound healing in standardized blister wound models compared to supportive couple interactions. The social signals a healing person receives alter the molecular environment in which their tissues are repairing. The body heals differently, depending on whether it feels safe. The process of immune tolerance, the immune system's learned capacity to recognize the body's own tissues and refrain from attacking them, is established during early development through a process that involves deliberately exposing developing T cells to self-antigens in the thymus and eliminating those that react to them. This process, called negative selection, removes potentially self-reactive immune cells through apoptosis. The immune system must eliminate a significant portion of its developing cells to build a functional, self-tolerant immune repertoire. The immune competence of an adult depends on the deliberate deletion of cells during development. The healthy body is partly built of what was removed. The biological concept of resolution is now understood as an active, molecularly driven process rather than a passive cessation of inflammation. For decades, inflammation resolution was assumed to simply result from removal of the inflammatory stimulus. Research from the 2000s onward, led in part by Charles Sirhan, established that resolution requires the production of specific signaling molecules, lipoxins, resolvins, protectins, and myosins, that actively drive each step of the resolving process. Neutrophil, apoptosis, macrophage, efferocytosis of apoptotic cells, vascular restoration, and tissue remodeling initiation. Without active resolution signaling, the inflammatory response does not stop. The end of the worsening phase requires as much biological effort as its beginning. The healing of peripheral nerves after injury is among the slowest repair processes in the human body, and the rate of regrowth is set by a biological constraint that no current intervention can accelerate. Axons regrow at a rate of approximately 1 millimeter per day, roughly 1 inch per month. A nerve injury in the forearm may require 2 to 3 years before sensation and function are fully restored. During this regrowth period, the patient may experience tingling or hypersensitivity, the nerve arriving in stages, making partial contact before fully reaching its target. The pace does not change because the waiting is difficult. Psychological processing of difficult experience involves a form of neural remodeling partially mapped through neuroimaging studies of people in therapy. The hippocampus, involved in contextualizing memory, shows measurable changes in volume and activity in people who recover from depression and PTSD compared to those who do not. Research from King's College London found that effective therapy for PTSD was associated with reduced amygdala hyperreactivity and improved prefrontal cortex regulation over the course of treatment. These neural changes took months to emerge and were not visible in the early weeks, the period when clients typically report feeling worse. The remodeling was running beneath the surface all along. The body's circadian rhythm, the approximately 24-hour biological clock, plays a significant role in the timing of healing processes. Many aspects of the immune response have circadian peaks. Neutrophil activity is higher in the morning. Natural killer cell activity peaks in the evening, and certain cytokines follow distinct daily rhythms. Research, including animal model studies and some human data, suggests that injuries sustained during the biological day may heal faster than those sustained at night, because the inflammatory and repair machinery is at its daily peak when the wound occurs. The circadian rhythm is not just a sleep schedule, it is a repair schedule. 75 facts in, the intellectual answer to the central question is clear. The body runs a mandatory damage protocol before every act of repair, because the repair is architecturally downstream of the clearing. Inflammation is not preparation for healing. It is the first phase of healing. The pain, swelling, temporary dysfunction, and systemic disruption are not the cost of healing. They are the mechanism. Healing is not linear because biology is not linear. Your body must destroy before it builds. And every symptom of worsening is a signed work order. The remaining facts move toward what this means for the body you live in. Tonight, breathe slowly. the repair that has been running across every scale we've visited tonight. Cell, tissue, organ, nervous system, mind, is running this very same logic in you, right now. You don't have to earn what your body does in the quiet. You only have to stop long enough to let it run. We're almost there now. The body does not heal on a timeline you set for it. It heals on a timeline set by cell biology, cytokine kinetics, collagen maturation rates, and nerve regrowth speeds. Processes running on their own schedules for hundreds of millions of years before anyone asked them to hurry. What you can do is provide the conditions they need. What you cannot do is negotiate the pace. What feels like regression is often the beginning of the next phase. The muscle most sore on day 3 is the muscle that will be stronger at week 12. The nervous system that feels most raw in the first weeks of therapy is the one most actively rewriting its circuits. The discomfort and the progress are not opposites. In most cases, they are the same event. The pain of healing does not mean the healing has stopped. In most cases, it means the healing has started. The absence of pain during tissue repair is often a sign of inadequate inflammatory response, not of smooth progress. What feels like the problem running is frequently the solution arriving. The two are often the same signal. Read differently depending on whether you know what phase you are in. Your immune system has been running the same 3-phase repair protocol: clear, build, remodel, since before your species had a name for it. It does not need to be explained. It does not need permission. It only needs the conditions that allow it to complete. Rest, adequate time, sufficient nutrition, and the absence of sustained threat. Those conditions are what you can give it. Sleep is one of the most significant conditions the healing body requires. Growth hormone pulses during slow-wave sleep. The glymphatic system addresses the day's metabolic accumulation. Emotional charge is processed and reduced during REM. Every hour of adequate sleep is a direct contribution to the repair that is currently in progress, not a reward for the day. A condition the repair requires. The body heals differently when it feels safe. Social connection, perceived support, and the absence of sustained threat reduce baseline cortisol, improve macrophage function, and accelerate the inflammatory to proliferative transition. The experience of safety is, at the molecular level, measurably anti-inflammatory. The people around you while you heal are not peripheral to the process. They are part of the repair biochemistry. The cells doing the work of repair do not know you are impatient with them. They are proceeding at the rate set by diffusion gradients, receptor binding kinetics, and gene expression timelines. The biology is not slow. It is precise. It is also indifferent to urgency. You cannot persuade it to move faster. You can only stop making it start over. Chronic wounds, injuries that fail to heal because the clearing phase keeps restarting, are the clearest biological evidence of what happens when resolution is prevented. The body is not failing. It is running the first phase, over and over, waiting for the conditions that allow it to move to the second. The treatment for a chronic wound is rarely more intervention. It is more often the removal of what keeps interrupting. The remodeling phase of healing, the longest phase, is invisible from the outside. No swelling, no redness, no obvious signs that anything is happening. The tissue is quietly reorganizing the architecture of its collagen, aligning fibers, adjusting density. Healing does not stop when it becomes quiet. It often deepens then. The visible phase was preparation. This is the work. Post-traumatic growth, documented across thousands of people who have moved through significant adversity, is not a consolation prize for suffering. It is a genuine expansion of capacity, new relational depth, new tolerance for uncertainty, new access to meaning, that only became available after the disruption created the space for it. The space was real. So is what grows there. The body's active resolution signaling, the lipoxins, resolvins, and protectins that drive inflammation to its close, is produced from omega-3 fatty acids found in fish, flaxseed, and walnuts. What you provide your body matters at the molecular level. The machinery for completing the repair protocol requires the substrate to run it. The end of worsening is built from what you gave the body to work with. Nerves regrowing at 1 millimeter per day do not speed up because the waiting is uncomfortable. The pace is set by the biology of axonal transport, cytoskeletal assembly, and Schwann cell guidance. But the destination is reached at that pace, if the conditions for regrowth are maintained. 1 millimeter per day, across months and years, adds up to something fully restored. The emotional clearing that precedes psychological integration follows the same phased biology as the physical clearing that precedes tissue repair. The difficult feelings are not obstacles to healing. In most cases, they are the clearing in progress, the emotional equivalent of the inflammatory phase, running its necessary and time-bound course before what comes next can begin to take shape. What the body asks of you during healing is not complicated. It asks for adequate sleep, sufficient nutrition, reduced threat where possible, time. These are not luxuries or rewards. They are the substrate of a repair protocol that cannot complete without them. The body does not need you to do more. It needs you to stop removing what it requires. The macrophages that switched from M1 to M2 phenotype in your tissue, from clearing to building, did so silently, without any sensation you could name. Most of what the body does to repair itself happens entirely outside awareness. You feel the edges of it, in discomfort and fatigue, and the slow return of function. The work itself is larger and quieter than what reaches you. Bone that has been repeatedly stressed, recovered, and stressed again is measurably denser than bone that has never been challenged. The architecture of repaired bone is oriented along lines of force, built specifically for the demands it will face. The body does not just restore what was lost. Given the right cycle of damage and recovery, it builds beyond the baseline. The repair can exceed the original. The nervous system that has been through hyperactivation and regulated recovery does not return to its previous configuration. It arrives at a recalibrated state, one that has passed through the difficulty and reorganized around the experience. In many documented cases, it is more flexible, more tolerant of uncertainty, more capable of containing difficulty without being overwhelmed. The original is gone. What returns is more capable. The three-phase repair sequence: clear, build, remodel, has been running in your body since before you were born. Every tissue you carry was built through this process. The skin you are in, the bones that hold you upright, the neural circuits processing this moment, all of it passed through a version of controlled worsening to exist in the form it has now. The discomfort of healing is not asking you to fix anything. It is asking you to continue providing the conditions that allow it to finish. Rest warmth. Enough stillness that the repair does not keep restarting. Not heroic effort. Not perfect conditions. Just enough quiet and enough time for the protocol to run through to its natural end on its own terms. Resolvins and protectins, the molecular signals that drive inflammation to its close, are made from what the body already has, if given the conditions to make them. The end of worsening is not imposed from outside. It arises from within, when the clearing has been allowed to complete. The body carries its own resolution. It only needs the circumstances to use it. The body you are resting in right now has repaired itself from things you have long since forgotten. Injuries that seemed significant at the time. Illnesses that disrupted weeks. Neural circuits that needed months to reorganize. The evidence of its capacity is the simple fact that you are here, in this moment, resting, quiet enough to hear these words. Healing is not something that happens to you. It is something your body is doing, continuously, at every scale, with or without your awareness or cooperation. Your contribution is not to accelerate it or manage it. Your contribution is to stop adding to what it has to repair and to provide the conditions it was built to use. That is enough. The signed work order, the symptom of worsening, does not mean the contractor has failed. It means the work has begun. The mess is the evidence of construction. The clearing is the evidence that what comes next will have a clean foundation to build from. Nothing has gone wrong. The sequence is running. That is what worsening means. The body's capacity for repair is older than consciousness, older than language, older than any explanation of it. It was running long before anyone understood it. It runs, tonight, in the quiet, in the space behind these words, following its own ancient and reliable sequence. You did not design it or teach it. You inherited it. It has never needed your supervision. The answer to the central question is not a scientific conclusion. It is something more personal. The body runs its mandatory damage protocol because that is the only architecture for repair that works. What breaks when we interrupt it is not just tissue or nerve. What breaks is the trust that the worsening is part of the process. Tonight, that trust has a foundation. The body has been completing its work orders, quietly, for as long as you have been alive. Something shifted over the course of these 100 facts. Not the facts themselves. Facts about cytokines and collagen and macrophage phenotypes. Something larger than that. The understanding that the body does not fail when it worsens. It begins. The inflammation that arrived before repair. The nerve that had to degenerate before it could regrow. The bone that had to be made temporarily weaker by the microfracture that would eventually make it stronger. All of it following the same signed sequence. Healing is not linear because biology is not linear. Your body must destroy before it builds. And every symptom of worsening is a signed work order. That was always true. Tonight, it has 100 facts behind it. The Sleepy Psychology Facts playlist has been moving through the biology of what happens inside us, one mechanism at a time. The next video follows the part of the map that tonight only pointed toward. What the body does when the repair is complete, and the question of what remains. That video is waiting whenever you are ready. Something is already releasing. Not because you did anything, because you stopped long enough for it to begin. Let your body give itself over to what it already knows how to do. If sleep comes, it carries you into the part of the repair that needed you to stop first. The phase that only runs when the day has gone quiet. But if your eyes are closed, stay there. Rest well, weary one. Every symptom of worsening you ever carried was a signed work order. The work was always underway. Fall asleep to gentle facts, where science meets sleep. Good night.